Welcome to the Explainer. Today we are cracking the code on chemical equations. Okay, so let's dive right into this secret language that chemists use to write the recipes that make up our entire world. So let's start with a bit of a mystery, right? A firework, a rusty nail, and your own digestion. On the surface, these things seem totally unrelated. But I promise you, by the end of this, you'll see how they are all driven by the exact same fundamental process.
You know, the key to solving our little mystery is learning how to spot the clues of a chemical change. This isn't just about something changing its form, like ice melting into water. No, this is about substances transforming into entirely new things. So let's put on our detective hats.
One of the most common signs that something new is being made is, the appearance of a gas. Just think about dropping one of those fizzy antacid tablets in a glass of water. All those bubbles? That's your first big clue that a chemical reaction is happening right there.
And here's a classic example from the lab. You take some zinc granules, mix them with acid, and boom, you get bubbles of pure hydrogen gas. And that little pop you'd hear if you brought a match close, that right there is the sound of chemistry in action.
Now for a really cool one. You know, sometimes you can mix two perfectly clear liquids together and almost like magic, a solid material just appears and settles to the bottom. In chemistry, we have a name for this solid. It's called a precipitate. Look at this. Here we're mixing solutions of sodium sulfate and barium chloride, and instantly this cloudy, white solid forms. It's incredible. Two liquids just rearrange their atoms to create something entirely new. And finally, a temperature change is a dead giveaway. If a reaction gets hot, like that firework we saw earlier, we call it exothermic. It's releasing energy. But if it gets cold, it's endothermic. It's actually absorbing energy. Either way, it signals a chemical transformation is happening.
Okay, so we found our clues, we know a reaction is happening, but trying to describe it in a full sentence is frankly pretty clumsy and inefficient. Chemists needed a better way, a kind of shorthand to write down their recipes.
Just trying to describe a reaction in a full sentence is a mouthful. A word equation, on the other hand, is so much cleaner. We just list our starting ingredients, use an arrow to show the change, and list our final product on the right. Simple. But you know what? We can do even better. To make this a truly universal language, we swap out the words for chemical formulas. Now, any chemist, anywhere in the world, knows exactly what CaO and H2O are. The goal here is maximum information in the minimum amount of space.
And the structure is always simple and consistent. On the left, you've got your reactants. Think of them as your starting ingredients. That arrow in the middle means yields or produces, and on the right, you get your products, the new stuff you've made. This is really the basic grammar of chemistry.
There's just one tiny problem. Our new sleek chemical equation is actually breaking a fundamental law of the universe. Seriously, it's an incomplete recipe, and we absolutely have to fix it.
And here it is. This is that law, the law of conservation of mass. It's one of the most important rules in all of science. What it means is you can't just have atoms appearing out of nowhere or vanishing into thin air. Whatever you start with, you have to end with, just rearranged.
So this brings us to the most important part of writing the recipe. It has to be balanced. We've got to make sure the number of atoms of each and every element is exactly the same on both the reactant side and the product side.
Okay, so take a look at this unbalanced equation. See the problem? We start with 2 iron atoms on the left, but we only end up with 1 on the right. And we start with 1 aluminum atom, but somehow end up with 2. This recipe is breaking the law.
So how do we fix it? Well, we follow these simple steps. It's kind of like a puzzle. We can't change the formulas themselves. That would be like changing the ingredients in our recipe. But what we can do is change the amount of each ingredient by adding these little numbers called coefficients out front. And voila! By putting a 2 in front of the aluminum on the left and a 2 in front of the iron on the right, everything lines up perfectly. We now have 2 irons, 2 aluminums, and 3 oxygens on both sides. The law is satisfied. Our recipe is now correct. All right, our equation is balanced and it's correct, but we can still add a few more details to make it even more informative, to really tell the complete story of exactly what's happening.
Chemists use these simple symbols to add some really crucial context. They tell us the physical state of each substance. Is it a solid, a liquid, a gas, and even other things, like whether heat was needed to get the reaction going. So putting it all together, our final equation tells a really complete story. That little S shows us that solid iron oxide reacts with solid aluminum to produce solid iron and solid aluminum oxide. See? This isn't just a list of elements anymore, it's a detailed description of a real-world event.
So, we've learned the code, we can spot a reaction, we can write it down, we can balance it. But why is this so important? I mean, why does this all matter? Because a balanced equation isn't just descriptive, it's also powerfully predictive.
So what do I mean by predictive power? Well, it lets us answer very specific real-world questions. For instance, this number right here, 540 kilograms, is the answer to a huge industrial problem, and it's an answer we can get directly from that balanced equation we just created.
You see, our balance recipe gives us the exact ratio of the atoms. By converting those atomic ratios to mass, an engineer can calculate that to produce 1,120 kilograms of iron, they need precisely 540 kilograms of aluminum. This isn't guesswork at all. It's the quantitative power of chemistry that builds everything from new medicines to rocket fuel.
This universal language doesn't just describe the world around us, it allows us to engineer it. It gives us the power to combine elements in predictable ways to create brand new materials and solutions. So the question isn't just what reactions already exist, but what amazing new reactions can we design for the future?